Hello. In this presentation, I'm going to talk about the use of abstract controller design methods in stabilization and other control design for partial differential equations. And for PDE systems with boundary inputs and outputs, I'm going to demonstrate the benefits of use of boundary control systems as the abstract framework. If we consider a simple PDE example, a wave equation, which will be our running example throughout the talk. This is a model which describes, for instance, the dynamics of a vibrating string on an interval of a fixed length, now from 0 to 1. And at one end of the spatial interval, we have a Neumann boundary condition, a homogeneous one, and at the other end we have a force input which allows us to move the string. So this is a Neumann type boundary input. On the other hand, we measure the position and the velocity at the other end point of the spatial interval. And based on this information, we would like to construct a stabilizing output feedback control in such a way that the state of the wave, meaning the deflection profile and the velocity profile, converge to 0 as t goes to infinity in an appropriate sense. And now we have a so-called non-collocated situation where the input and the output affect different endpoints of the spatial interval of the string. And because of this, we know that we have to use dynamic controller design because static output feedback will not give us the bit. And when we start our controller design process, we have at least two options how to proceed. One option is to work directly with the PDE, and based on the equations of the wave system, we can guess what kind of an observer-based controller we could design by adding some output injections to a copy of this system, and finally show with mathematical techniques how we get closed loop stability. If we want to use abstract infinite dimensional systems as a basis for our controller design, the workflow is as follows. We first begin by representing our wave equation as an infinite dimensional system on an appropriate Hilbert space and within a suitable class of abstract systems. Then we would go into the literature and find a controller design result which is applicable for this abstract class of systems that we're working with. This gives us a general controller structure, and it also gives us information on how we should choose or tune the parameters of our controller in such a way that it fits the wave equation we're studying. And then the same result would also guarantee closed loop stability provided that these parameters are chosen in an appropriate way. And the controller we designed this way is also an abstract control system. And in order to get final controller, which is also a PDE model, we would want to reinterpret our abstract controller as a PDE. If we take a little bit closer look at the process, but still staying on a very formal level, we first start by choosing a state for our wave equation in the abstract framework. What we can do for the wave equation is to choose a state vector consisting of the deflection profile and the velocity profile. And this way we can represent our system on the product space consisting of the first order Sobolev space for the deflection and L2 for the velocity profile. With these choices, we can roughly represent our system in the form of a system with A, B, and C as infinite dimensional operators. For such linear systems, we could apply a general controller design result, which says that if we choose a controller which is a copy of our original system with A, B, and C all making an appearance, but with an additional output injection term, then this kind of a controller can help us achieve closed loop stability. Here, the parameters of the controller are the operators K and L. One is a state feedback gain and one is an output injection. And these should be chosen in the tuning step in such a way that A plus BK and A plus LC correspond to systems with exponentially stable dynamics. And if this is possible, then our controller stabilizes the system. In the tuning step, indeed, choosing our K and L would correspond to considering versions of our system where we only have either state feedback or just output injection. And in the choosing of these parameters, we can apply PDE techniques by first reinterpreting these equations as copies of the wave equation. Finally, we would like to convert our abstract controller to a PDE. And since our original system describes a wave equation, also it's reasonable to assume that the controller, which is a copy of our plant, is also a wave-type PDE. And this way we arrive at our final controller. The benefits of this approach is that the controller design result always gives us a clear structure of how to choose our controller. We don't need to do any design work for this. And it also guarantees the closed loop stability. What we need to do in the process is to tune the parameters K and L of our controller, so to stabilize these two versions of the wave equation. But this is in general easier than proving the full closed loop stability of the PDE with a PDE controller directly. And this is a generic approach. This works in a very similar way for several different kinds of PDE. The main downsides of this approach is that when we consider PDEs with boundary inputs and outputs, already the first step where we represent the PDE as an abstract control system can be really challenging. This is because in the ABC formulation of our system, the operator B is unbounded in the sense that its range is not contained in the state space, but instead we have to build a bigger space for it. And finding what this B operator is can be really demanding, especially in the case where PDE is a multidimensional model. This often leads to the situation where we need to choose a very general class of abstract linear systems. And these are quite demanding to handle or even read the associated results. So if you want to apply this method, it often seems like you have to be a master in both PDE analysis and functional analysis to solve the original control problem. And this is definitely not ideal. The other question is, can we find available control design result for our abstract class? These get more and more rare as the generality increases. And also the final step of reinterpreting the controller as a PDE system has the same challenges as the first representation step. What I propose in this talk is that we can mitigate some of these challenges by choosing an appropriate class of systems which is already tuned to the special properties of PDEs with boundary inputs and outputs. And these are called abstract boundary control systems, and they have the general form shown here. We can do such a representation for the wave equation with the same state variable and the same state space as before. And the way we can do this is we can simply expand our wave equation to a first order system and then do a side-by-side comparison between the 3 lines in the wave equation and the 3 lines in the abstract representation. Indeed, formally, the first lines are identical, so we have the time derivative of our state variable on the left-hand side, and on the right-hand side we have some differential operation on our state variable. So choosing our operator A as the typical wave operator gives us the validity of the first line in the abstract representation. On the other hand, in the second line of the abstract control system, we have some kind of a evaluation of the state variable through a boundary trace operator B, and this should be identical to application of the control input U on the right hand side. And indeed, if we look at how the wave equation, boundary control and boundary conditions work, on the left hand side we indeed have a boundary trace evaluation of our state variable at points 0 and 1 of the spatial interval. So if we choose our B to be an operator which takes the first state component, differentiates it, and then evaluates it at the endpoints of the spatial interval, we have the exact match between the left-hand sides of the wave equation, the abstract representation. On the other hand, Q and U we can choose exactly like in the wave equation, so Q is just a matrix. Finally, on the last line, we just have the output of the system, again given by a boundary trace evaluation of our original state variable, and by choosing a boundary trace which evaluates both components of the state variable at 1, we obtain identity of the third lines. And so this way we get this kind of abstract representation for our wave equation. And we can now look at what are the characteristic properties of these operators involved. So A, B, C are all linear operators. A is an unbounded operator, here a differential operator. B and C are unbounded operators, but they are nevertheless relatively bounded with respect to A. And finally, Q is just a bounded operator, here in our wave case a matrix. And on the other hand, if we set U to be equal to 0, replacing this QU term with 0, we get dynamics which correspond to the wave equation with homogeneous Neumann boundary conditions. We know that this operator then generates a strongly continuous semigroup on the space X. And finally, the operator B is a surjective operator which also has a bounded right inverse mapping from C to the domain of A. And these are very important properties of the operators that we found for the wave equation, but more generally, if these conditions hold, then we say that the tuple consisting of the operators in our boundary control system is a boundary node on the Hilbert space X. So as we can see from the construction of the wave equations abstract representation, all operators A, B, C, and Q of the system can be relatively easily identified. This is because the operator B on the left-hand side of the second equation is now a boundary trace operator, and it does not have to be inverted in order to make it appear on the right-hand side of the first equation. And similarly, if we have a boundary control representation in the abstract domain, it is relatively straightforward to describe this as a PDE system. So the main question is then, why doesn't everybody already use these techniques that I'm proposing here? Boundary control systems are not a new invention. They go back to at least the 1980s. But they have been much less developed compared to the theory of well-posed systems and regular linear systems over the years, so they have less results available. But this is something that can easily change, and with a bit of work we can develop very good results for boundary control systems as well. I'll show you how. The first thing we might be interested in, does our equation have solutions and under what conditions? Our first result is that the equation has a very large class of classical solutions. So if our initial state belongs to the domain of our differential operator and u is at least twice continuously differentiable in such a way that our boundary condition at the second line holds at time 0, then our system indeed has a unique classical solution in the sense that x is a continuously differentiable function, and these three equations hold in the exact sense written here for all times. And with these classical solutions, we can define the so-called well-posedness of our boundary node. We say that a boundary node is well-posed if the state and output of this system depend continuously on the initial state x0 as well as on the input of the system. And this coincides exactly with external well-posedness of any PDE system or any other abstract class of systems. And well-posed boundary nodes are a especially nice class of systems to work with. First of all, we can then define larger class of solutions, generalized solutions and mild solutions. In addition, the mappings from the initial state and the input to the state and the output of the system define a so-called well-posed linear system. This is a class of abstract systems that is understood very well, and this allows us to tap into this existing literature on well-posed systems and bring back results which are then applicable for our boundary control system as well. Another very important and useful concept for any linear system is the transfer function of our system. And for a boundary control system, we can define it based on a solution of this so-called abstract elliptic equation, which looks a lot like our original system, but where our time differentiation is replaced by the multiplication with the frequency parameter. And this means exactly that computation of the transfer function of our boundary control system coincides with taking a formal Laplace transform of our original PDE system. So we can often compute and in the rest of the cases analyze the transfer function based on just the formal Laplace transform of our original PDE. So on to the controller design. So if we want to stabilize a boundary control system in a dynamic manner, we can use again an observer-based controller which looks like a copy of the original system but with some additional output injections shown here. The output injections can appear in at least two different places. They can appear in the first state equation as through a bounded input operator Li, or maybe more interestingly, they can appear in the boundary conditions of the system as additional boundary inputs. I'm not going to talk much about these distributed injections. If you look at my preprint, you will see more of these, but instead I'll just focus on the boundary injections right now. Here again, these L and Li are the appropriate output injection gains, and the output of the system is determined by a state feedback gain, which has the role of an output operator in the controller. And our main stabilization result there is as follows. We assume that we consider a well-posed boundary control system. In addition to the well-posedness of the original system, we assume that we also have well-posedness if we add the state feedback gain as an additional output of the system and the output injection as an additional input in the system. Our main assumption is again on stability of two systems which are associated with just pure state feedback and output injections respectively. So these systems, AK and AL, correspond to the boundary control system where we have applied stabilizing state feedback or just output injections with operators L and Li. In addition to achieving stability of these two systems, we want K, L and Li to satisfy a condition related to the transfer functions of two systems. In the first one, we replace the original output operator with the state feedback gain to arrive at the transfer function pk. And for this transfer function, we assume that these inverses shown here exist and are uniformly bounded on some right half plane of the complex plane. And we also have a completely analogous condition for the transfer functions PL, which are obtained from the original system by replacing the original input with the output injection. And if these conditions hold, then we have exponential stability for the closed loop system. So let's take a look at how we can apply our result in the context of the wave equation. We already saw that we can represent in the first step our wave equation as an abstract boundary control system. We can also apply direct analysis based on existing PDE results to show that this boundary node associated with the wave equation is well posed. This means that we are in a position to apply our abstract stabilization result. In the parameter tuning step, we would like to find the state feedback gain K and the output injections L. In the case of the state feedback gain, we can convert our abstract system with the state feedback back to a wave equation of this form, where we have Neumann boundary conditions and a Neumann boundary feedback. And here we can apply, for instance, backstepping techniques or existing results to choose k in such a way that it stabilizes both the velocity and the deflection profile of the wave equation. And we can also show that this choice of k satisfies this requirement for the transfer function pk in our result. Similarly, we can also use PDE-based techniques to stabilize the copy of our system with pure output injections to arrive at the choice of our output injection operator L. In the final step then, we take a look at our abstract controller and convert it back to a PDE. And as mentioned, in the context of boundary control systems, this is relatively easy to identify as another wave equation, which is a copy of our original system, but with additional output injections, and the output of our controller is defined as a suitable boundary trace of the state of the controller. With suitable choices of the scalar parameters appearing in the equations, we get exponential stability of our closed loop system. So to summarize, if we apply the abstract approach in stabilization or control of PDEs, it begins by representing the PDE as a system within an appropriate class of abstract systems. Then we can apply a general abstract controller design result. The parameters of this control need to be chosen in such a way that they fit our original PDE model. Here in this case we were choosing the state feedback and output injection gains. And finally, our abstract controller, which achieves closed loop stability, has to be converted into a PDE system to arrive at a PDE controller. And as I've demonstrated, this can be challenging in the case of PDEs with boundary inputs and outputs, but we can affect the level of the challenge with our choice of the framework. And I believe that boundary control systems can offer a lot in this regard. So thank you very much for listening.